Discrete Markov change. In discrete Markov chain model, transition can only occur at the end of the period. We are going to take disability income model as examples in this chapter. So, let's denote. Let yt be the state at time t. I'll remind you again, in the disability income model you have healthy, and then you have disabled, which is state 1, and that. This can go from here to here, here to here, and then here can come back to here. So the state space for the disability income model here, the state space say this state space gonna be state 0, 1 and 2. The probability of a person's going from state 0 to state 1, state 1 to state 0, state 0 to state 2, or state 1 to state 2, this one we are going to denote it as Pij. This is the probability of going from state I to state J at time t. This will be equals to probability of, given that the person at state t is equals to I, then the person will be in state J at yt plus 1. Let's draw timeline to show this one clearer, so that it become clearer to you. Let's say this is y0 at time y0, at time y1, at time y2. We can continue more, but I will stop until y2. So for disability income, usually when you are buying into the policy, you are in healthy state, and then you can maintain in a healthy state after a year, or you can transit into state 1, or you can transit into state 2. In year 1, if you are in state 0, you can still maintain in state 0 in year 2, or you can go into state 1, or you can go into state 2. If you are in state 1 in year 1, you can go into state 0, or maintaining in state 1, or can go into state 2. If state 2, you can't go anywhere, because there you will be maintaining there. Okay, so this is what it meant by this probability above. So in state at time y0, you are in state I. For here I is 0, and then you are going to be in state J. For here it will be 0. Okay, and if going to state 1, it will be, your J here would be 1. If going to state 2, your J would be 2, and so on. Okay, so the probability of these transitions, we can also write it in terms of matrix, because it is a lot. So if you only have 3, then you can probably, it will not be complicated. But if you have like 10, hundreds, then it will be difficult if you have like 100 states. So you can write this in terms of matrix, transitions matrix, probability transitions matrix, where we denote it as capital P at time t transits from state I to state j equals to probability of t transit from state 0 to state 0, probability of t transit from state 0 to state 1, probability of t transit from state 0 to state 2, up until state n. And then here would be from state 1 to 0, and then it will continue until n. Here also will continue probability of state n going to state 0, or probability of state n maintaining in n. This is the transitions probability matrix. Loosely speaking, we can say that Markov means what? Given the present, you can forget whatever happened in the past. So we know that the Markov property are ignoring whatever happened in the past. We can write the probability of state at time t plus 1 equals to j, given that you know that you are in state t at time state I at time t, and you are in state I t minus 1 when you at time t y t minus 1, and you are at state I t minus 2, and so on. This will be equals to probability of yt plus 1 equals to j, given that yt equals to I. The rest of this can be dropped. You can drop the rest of this. This is what Markov property said. Okay, we will continue with the disability income examples. Let's say that you have a probability of the transitions matrix as equals to 0.7, 0.1, 0.2, 0.3, 0.6, 0.1, 0, 0, 1. This 0.7 means that it's transiting from state 0 and maintaining in state 0 with the probability of 0.7. This will be happening at time t. Okay, and then here would be 0.3 would be transiting from state 1 to state 0, and then here is state 2 to state 0. The probability is 0 because state 2 for the disability income is death. You cannot go from death to healthy. Disability income model. Okay, I draw to you again. It will be state 0, state 1, state 2. This is disabled. This will be that. This is healthy. and then it can come back to here. Okay, so let's assume that I'll write here probability of t, the matrix for transition matrix probability at time t equals to the transition matrix for the probability transition matrix for t minus 3 plus 1 equals to the transitions probability matrix for t plus 2 equals to, and so on. So this probability we call when pt equals to pt plus 1 equals to pt plus 2 and so on, we call this homogeneous, where pt is independent of the time. When pt not equals to pt plus 1, not equals to pt plus 2, and all pt are different, or pt is dependent on time, we call it inhomogeneous. Okay, I'll write it here. pt not equals to pt plus 1, not equals to pt plus 2, and so on. This is inhomogeneous. That means that your probability transitions matrix is depending on time. Okay, let's use these examples. So at time 0, for the disability income, a person can be in state 0, and then from state 0 can remain in state 0 at time 1, and then can go to state 1, and also can go to state 2. The probability of going to state 0 here, it will be as per stated here. Maintaining in state 0 will be 0.7, 0.1, 0.2, and then from year 1 to year 2, the probability of maintaining will be, maintaining at 0 would be 0.7, going to 1 would be 0.1, and going to 2 would be 0.2. And then from state 1, you can also go to 0, 1, and 2. Okay, this would be 0.3, 0.6, and 0.1. And then from state 2, it will maintain in state 2. This would be 1. State 2 here, you see, it cannot go to other state. Once you go to state 2, it will be there forever. So we call this as absorbing state. Your state 2 is the absorbing state. You look at this timeline, you look at the probability of going from year 0 to year 1 will be similar from one state to another state as it is in year 1 to year 2. It does not change. For this case, we call it homogeneous. When it change, this probability change, instead of 0.7, for examples, let it change to let me change the pen color first. Okay, let's say it is no longer 0.7. Here, for example, maybe it becomes 0.6, 0.2, 0.2, and this one is no longer this. It will change it to probably 0.2, 0.5, 0.3. Then we call this the green probability with this the first probability. The probability in the first year and the probability in the second year are not similar, so we call this inhomogeneous. Okay, that's it for discrete time Markov change. We will continue in the next video. Thank you.